In the previous episode, we used a little 6BE6 heptode to create a NAND gate. And that was awesome because a NAND gate is a universal logic gate. What this means is that we can build any other logic gate through a combination of NAND gates. But I only had, 8 or 10 of these little 6B6 heptodes. And if I want to create some complex logic, I need to stack a bunch of logic gates on top of each other. And, well, only having 8 or 10 tubes that's just not going to cut it. But it just so happens that there's one more universal logic gate, and that is the NOR gate. And so what this means is that we can build any other logic gate through a combination of just NOR gates. This is awesome. But what's even better is that we can build a NOR gate really easily. All we have to do is put an OR gate before one of our inverting amplifiers. And building an OR gate is even easier. We just take two diodes and connect their outputs together, and that's an OR gate. So we already have all the ingredients to create a really simple NOR gate. But I'm not just going to stop at creating a NOR gate, because ultimately we want to create something interesting. Just creating a single logic gate in and of itself is fun, but it doesn't get us anywhere. So today I wanted to make an SR latch, which is called a set reset latch. It's a latch or a flip-flop. You can hear them called many different things. And I actually have 3 SR latches that I want to take a look at. All 3 of them are on the breadboard, and we're going to go through them one at a time. Each one is made slightly differently. And so what we'll do is we'll break them down one at a time and take a look at them in more detail. But first we got to hop over to the bench. The first thing we need to do is build an OR gate, and that's actually really easy. We can do it with just 2 diodes. We just take 2 diodes, connect their outputs together, and that becomes our logic output. And then the other ends of the diodes are our logic inputs, A, B, and Q here for our simple diode OR gate. This is super easy, and it's actually really easy to build with vacuum tubes as well. So if you remember, a simple vacuum tube diode has a plate and a cathode, and well, that's it. So if we take 2 of these and we connect the cathodes together, that becomes our Q output, and then we can have the plates be our inputs. There we go, A, B, and Q. That's our simple OR gate. And then to change this into a NOR gate, all we have to do is, well, invert this output right here. And we can do that with a triode, a pentode, pretty much whatever we can get our hands on, because building an inverting amplifier is one of the easier things to do with vacuum tubes. And if you remember, we set it up with just a simple plate resistor that feeds into, well, the plate. And then I'm going to draw a triode here, which has just a single grid, and then the cathode down here. And so if we connect the cathode to ground, and we connect the grid up to our Q here, and we pull the output out of here, well, we've just created a NOR gate. That was super easy. That's great. Essentially, the way this works is that if both A and B are low, there's no current coming through Q here, and which means that our grid is not receiving any current. And so this, through a biasing network of resistors here, will be pulled low, which means that the triode won't be conducting. And if the triode's not conducting, our output here is pulled to the positive voltage here through our resistor here, and so this will be pretty much what our positive voltage is here. So 24 volts is what we've been running at. But if either A or B go high, they will bring the grid to a positive potential, which means that electrons will start flowing and the tube will start conducting. And that means that our output here will be pulled to a potential that's pretty close to the cathode, which happens to be ground. So that'll pull this to low. And that's a NOR gate. Now, I didn't draw in the resistor networks here that bias this to a negative voltage, but if you really want to see what those are, take a look at some of my previous videos. I go over those in a bit more detail. But instead of drawing all of this out every single time, instead we're just going to draw this symbol for NOR. And whenever I draw a NOR symbol, just know that it means this. And the symbol for a NOR gate looks like this. And in order to create an SR flip-flop, a set, reset, latch, or flip-flop, we really just need 2 NOR gates. So here we have our 2 NOR gates, and it's really pretty easy to build this. Essentially, we just take the output from one NOR gate, feed it into the input for the other NOR gate, and then take the output of that NOR gate, feed it into the input of the first NOR gate, and there we go. We have a set, reset, latch. This becomes our reset pin. This becomes our set pin, and then we have an output and we have an inverted output. So this output will always be the opposite of this output. And so if I put a positive signal into here, that will set the flip-flop into a certain state. And then if I put a positive signal into here, that will reset it to the previous state. And so this way we can create a flip-flop. This is awesome. This is actually kind of the basis of all memory. This is really cool. I think we can have a lot of fun playing with this. And so the 3 circuits that I have set up on the breadboard today are all 3 variants of this. They just go about it in slightly different ways. So let's pull the breadboard out and we'll take a look at it and see what the differences are between each of them. Okay, so here we have our breadboard set up, and I actually have all 3 SR latches already on here. This is actually the first one, these 4 tubes here. This tube is the second one, and this tube is the third one. And so we'll start by just looking at these 4 tubes here. And I've actually gone ahead and drawn out the wiring diagram, the schematic for how I laid these out, and I'll put that up on the screen here. You can see that the way it works is that we're actually using 2 pentodes and then 2 dual diodes. So each one of those diode tubes has 2 diodes in it. And then the 2 push button switches go into one of the diodes within the dual diode. And then the other diode goes over to the output of the opposite pentode. And then the pentode is set up just like an inverting amplifier. We've got our screen grid pulled high with a 100 ohm resistor. And then our combination of resistors here on the control grid, we got 2 33,000 ohms and a 4.7 thousand ohm resistor with a negative bias of negative 12 volts. And so you can see it's a fairly simple setup. You can actually see that even by looking at the board here, we don't actually have all that many resistors. It just takes up a lot of space from these vacuum tubes. And I have a little LED here on the end, and again I'm using a Zener diode to kind of shift the level to something that the LED is going to be a little more happy with. And well, I've got my vacuum tube voltmeter set up here, and I have it adjusted pretty well. So we'll take a look at the voltages, but I have the tubes on here, they're warmed up. Let's push these buttons and see what happens. Awesome, look at that. Our green light came on. And then if I push the other button, the green light goes off. Fantastic, that's awesome. That means that we have 2 functioning NOR gates here creating a set, reset, latch, or a set, reset, flip-flop, an SR latch. That's awesome, that's amazing. But, well, that's pretty interesting. If I push the button, you notice that the green light goes a little bright, and then when I let go of it, it comes a little dim. So, I'll tell you what, let's take a look at what the voltages are doing. We'll do that with our vacuum tube voltmeter here. And we'll take a look at this output here, this little, the output from this 6AU6 here on the end. And I've got this big yellow wire bringing it over to the diode over here, so we'll just go ahead and measure it at the diode side. That should be a little easier to see. Okay, there we go. All right, you can see that we've got, this is on the 30 volt scale, so that's just about 18 volts, just a hair under 18 volts. And that makes sense because our LED is on here. Now if I push the button here, that should reset it and turn our LED off. Oh, and it does, and look at that, awesome. We saw the needle swing down, and it went all the way down to, I don't know, about 6.5 volts. That's a pretty good swing. It looks like we've got just about an 18 volt to a 6.5 volt swing out of this. That's really cool. Now, remember I said that when I pushed the button, this LED got a little bright if I held the button. So let's see what happens when I do that. Oh, you can see, look at that. If I'm holding the button, we have about a 21 volt output. And then when I release it, then we drop down to about 18 volts. Well, that's interesting, but it works. It's awesome. I mean, that's technically 1 bit of memory. We have 1 bit of memory right here out of, granted, 4 vacuum tubes. This takes up a ton of space. It's huge. But you know what? I'm not actually against using small regular diodes. I mean, if we take a look at the old vacuum tube computers of yesteryear, the old IBM 604s is kind of the one that I reference a lot, but a lot of the old IBM vacuum tube computers used germanium diodes that were, you know, small, like a regular diode. And so I'm not against using that. And I think if we use just, you know, 4 diodes, we can eliminate 2 of these tubes. And then, if you remember, our 6DJ8 tube has 2 triodes inside of it. So we can actually combine both of our inverters into a single tube, which means that we could make the entire SR latch here out of just a single tube. And actually that's exactly what's going on the backside here. And so here is the schematic of how I wired up that. So you can see that in this schematic, it's laid out pretty close to the same, actually. Our resistor values are a little differently, and instead of having the screen grid and the suppressor grid to deal with, they're just not there. The resistor network coming off of our grids is a 4,700 ohm and then a 22,000 ohm and a 33,000 ohm, and that's biased again to negative 12 volts. And then instead of having the diode tube, we've got just 2 little regular diodes sitting there. And then one of those is for a push button, and then the other one comes from the output. Now on the outside of this schematic, we have these kind of 2 big semicircles, and you often see this in old schematics to denote that this is half of 1 single tube. So this is the right half of 1 tube, and then this is the left half of 1 tube. And so these 2 circles combine and make a single tube. And so this is just kind of an interesting way to draw a single tube in action. So I've gone ahead and I've turned around the breadboard here. And so, well, we've got 2 buttons, so let's push the buttons and see what happens. Hopefully it works. There we go, look at that. All right, our LED's on. Now it's not very bright. It is if I push and hold the button, but it's not very bright otherwise. Now if I push this button, that should turn the LED off. Yeah, awesome. Look at that. So the LED's on, the LED's off. Sweet, that works really well. But let's take a look at the voltages and see kind of what it's putting out. So we'll take a look at this one right here. All right, so that's our low. That's a logic low coming out of this. So that's pretty low. That's like a 3 volt output. Now if I push the button, look at that. We're not quite as high as we were on the previous one. And that's why our LED isn't quite as bright. We're at about 16.5 volts. So this is a 15 volt Zener diode. So it's clamping out quite a large amount of the voltage that's making it to the LED, which is why our LED is not that bright. But by looking at it here, we can see that we have actually a really pretty good swing here. We don't have as high of a max voltage, but we've got a really low logic low, and that is awesome. That makes stacking these tubes really easy because we don't run into problems with diminishing returns, and so that's fantastic. That's a really great logic low. Now if I push and hold the button, you can see that it's about the same. So we got about a 20.5 volt output if I'm holding the button, and I guess that's to be expected because we're piping 24 volts directly into it and pulling the grid a little higher than the actual output of the tube is doing it. But I mean, that's pretty awesome. That's really cool. All right, so there you go. We've made a SR latch out of a single tube, 1 bit of memory right there. But what's this extra tube doing over here? Why did I have 3 circuits? And actually, if you look a little closer at this one, you'll notice that there's no diodes in use on it at all. Well, now that's interesting. But actually, if we think about it, it's not that wild. This is actually just a bistable multivibrator. So here's the schematic for the third tube here. And you can see actually it's laid out a little bit differently. You can see that coming out of our grid, we go straight into the center of a resistor network. And then we have 200,000 ohm resistors creating kind of a voltage divider. And then we have 33,000 ohm for our input through our push button. And then the output just feeds into that top 100,000 ohm resistor on the other vacuum tube. And this is a much simpler layout. I mean, you can see that for this entire layout, we're using just 8 resistors. And that's actually a lot easier to put onto a breadboard or even onto a circuit board. Well, let's see how well it works on the breadboard here. Well, the LED's on, so if we push the button, the LED should turn off. There we go, our LED turned off. That's awesome. But check that out. If I push and hold the button, the LED brightness doesn't change. Well, that's interesting. So let's take a look at the actual voltage coming out of one of our outputs here. There we go. There's our output. So you can see actually we have a really pretty good output coming out of that. We've got about 19 volts coming out of that. That's awesome. All right, well, let's check our logic low. All right, now our logic low is actually a little higher than it was on this other tube. We've got about a 5.5 to 6 volt logic low, but that's actually still pretty low. So like a 20 volt to 6 volt swing is a really good swing out of it. That's super cool. Now that's an interesting thing actually. If I push and hold the button to turn it off, we go to a lower low. So we're actually getting a very similar effect that we were getting to the brighter LED on the other one, but we're getting it in the opposite direction. And again, I guess that makes sense because we're pulling the grid to an even higher voltage, which is kind of twisting our output on the opposing tube. Wow, now that's interesting. But what this means is that we have a really cool way of making 1 bit of memory, and we can do it really easily with some resistors. That's cool. That's really awesome. We have a lot of avenues that we can explore with that one. But there's one more thing that I want to check, and that is I only have a limited number of these 6DJ tubes, and we've seen that they work really well with what we're doing. But these are actually quite popular preamp tubes within the hi-fi audio community. And as such, they're kind of expensive. I got all of my 6DJ8s out of salvage, but if I were to buy some on eBay, they're quite expensive. They can go for a couple of dollars per tube, and if we need to stack up a whole lot of NOR gates, that can get real expensive real quick. But I have a bunch of other dual triodes, and if we look at a different dual triode, like this one, for example, this is a 6BZ7, and it's a dual triode, and the pin layout is actually identical to the 6DJ8. So I should be able to just plug this in to where the 6DJ8 is and be able to go from there. It should work, hopefully. So let's try that. I'll go ahead and flip the power supply off. We'll pull the 6DJ8 out. We'll slot in our little 6BZ7 here. There we go. We'll turn the power supply on. Give the tube a moment to warm up here. All right, now that the tube has warmed up for a little bit, let's push the button and see what happens. Well, okay, let's push the other button. Well, the light came on, but if I let go of the button, the light goes off again. It doesn't stay latched. Let's take a look at the voltage and see what's happening here. Okay, so, well, that's not inspiring. We're kind of right in the middle here. We're at about 13 volts-ish, maybe a little under 13 volts. Now, if I push this button, we do go low. You can see we drop to below 5, but then it immediately snaps back up to 13. And if I push this button, we go high. We go up to about 18, 19 volts, but if I let go of it, it snaps right back to 13. That's interesting. And that's also slightly disappointing because it means that I can't just change out for a cheaper tube. But actually, you know what, that's not all that surprising. Not all tubes are created equal. And this is a totally different tube, a 6BZ7. Even though it has the same layout, it's still a dual triode. You know, it would be wrong to assume that it would behave exactly the same as the 6DJ8. And so I think it's interesting that it behaves so differently, though. It didn't behave just slightly worse, it just didn't do its job at all. And so I think what we need to do is we need to kind of set up a test, and we need to go through and check all the different dual triodes I have and see how they respond and see what the differences are at just 24 volts. And so we'll have kind of a 24 volt dual triode vacuum tube shootout, if you will. But we'll save that for the next episode.